liquid-liquid extraction. So with my liquid-liquid extraction, this is a way to separate molecules. I have two liquids that are immiscible. It is important that you pick two solvents that are immiscible, so otherwise they'll mix and you'll just have a bigger solution. And I'm trying to pull some analyte, some compound of interest out of one solvent into another. So let's imagine this scenario. Suppose I have MTBE, this methyl tertiary butyl ether, and it's a nonpolar solvent, it's aprotic, and in it are dissolved benzyl and benzoic acid. Both those are relatively nonpolar. The benzoic acid is going to have to be protonated, so it'll be uncharged. You're not going to get charged compounds dissolving in nonpolar solvents. Benzyl is yellow, benzoic acid is colorless, and what I want to do is separate them for whatever reason, just because I said so. I don't like them being mixed, so I want to pull out the benzoic acid. Well, how do I do that? Okay, I could add water. MTB and water won't mix because one's polar, the other one's nonpolar. So I have my two liquids. And how do I get them out? Because benzyl and benzoic acid are both nonpolar. Well, one way I could do it is by adding a base. Why? Well, when I add a base, it reacts with benzoic acid. Benzyl is non-acidic, so it's not going to react to a base. Benzoic acid is acidic. So when I react it with a base, then it will get deprotonated and it'll dissolve into the water. So as I add this base, the benzoic acid travels up into the water, dissolves in the water. And so I've separated them out that way. And so I can do this successively to keep pulling out more and more benzoic acid if I want. Distillation is another way we could have potentially separated the benzyl and benzoic acid, assuming they both have reasonable boiling points. You'll usually do this when you want to separate liquids. And benzoic acid's not a liquid at room temperature. So for molecules that have very similar boiling points, distillation is usually a bad idea. The reason is because they'll both boil at roughly the same temperature, and then we won't be able to get them to separate. Distillation works best when the molecules in question have very different boiling points. Okay. So let's try out this practice problem. Okay, so 3 compounds are found in some mixture. How are they going to emerge in a distillation apparatus from first to last? Well, the first one that should come out should be the most nonpolar and or the smallest. And so that should be number 3. Why? Because although it has the same number of carbon atoms as number 1, it is the most branched. It has the smallest surface area to volume ratio. And as a result, its London dispersion forces will be weaker. And so it'll come out first. Number 2 should come out last because it's this carboxylic acid. And in fact, that actually helps me answer the question. But since number 2 is last, number 3 is first, my answer here must be B. Okay. Chiral resolution is another interesting analytical method or preparatory method. We talked about how enantiomers have very similar chemical properties, right? Because they're functionally the exact same molecule, just different stereochemistry. So it makes them really, really hard to separate. They have the same polarity, they have the same molecular weight. So we're not going to be able to separate them by these classical methods like distillation or liquid extraction, which are relying on molecules with different structural properties. So chiral resolution is a way to actually separate different enantiomers. And there's a couple different ways to do that. One is through crystallization. Some, but not all, enantiomers form enantiopure crystals. So we can try to crystallize them, and if we're lucky with the molecule in question, we'll end up with a pure enantiomer when the crystal forms. If that doesn't work, we can also use chiral as resolving agents. So these are reagents that are only going to react with a particular enantiomer, okay, due to some structural properties, and that's beyond the scope of the exam. It'll be described more in context if you need it. And that often results in some sort of precipitation. So then one enantiomer precipitates, the other one remains in solution, and then you can separate them. Okay. Next is chromatography. Chromatography is a really, really robust way of separating molecules. It can separate molecules based on polarity, based on size, based on charge, based on specific non-covalent interactions like antibody-antigen relationships. So very robust, used in a lot of different settings. At its core, it relies on a mobile phase and a stationary phase. Those phases refer to types of molecules which are going to either help move or help keep stationary the molecules. So to make it as concrete and relevant as possible, let's imagine a scenario. We have a scenario where we have a red and a green compound, and they're in a mixture. We want to separate them. And the two have slightly different polarities. One is slightly more polar than the other. So we want to try to separate them based on their polarity. How are we going to do it? Well, we're going to do that based on the column that we run it through and its specific polar properties. So I have some stationary phase, this solid matrix, which doesn't move, and some mobile phase, which will pass through, usually some liquid. So let's imagine that my stationary phase, the solid matrix that doesn't move, is polar. What I want my nonpolar phase to be is the mobile phase, right? One of them is going to be polar, the other one is going to be nonpolar. So what happens is when one is polar, the other is nonpolar, it doesn't actually matter which is which. It all depends on the particular method that you're running. When one is polar, the other is nonpolar, the molecules sort of get to choose. The one that's more polar spends more time with the polar one. The one that's more nonpolar spends more time with the nonpolar one. Since one of them is not moving and the other one is moving, it means they're going to travel through the column at different rates. So again, here I have a polar mobile phase. Let's imagine that. It's a polar mobile phase and a nonpolar stationary phase. So I pour my mixture in at the top, and over time they start to travel through, go down and down. And you'll see that they'll start to separate based on their polarities. Green starts to travel further and further down. What it tells me is that green is spending more time with the mobile phase because the mobile phase is passing through, and the red one is spending more time with the stationary phase. Like dissolves like, so the green one must be more like the mobile phase. The red one must be more like the stationary phase. So again, if the mobile phase was polar and the stationary phase is nonpolar, which of these compounds is more polar? The red one or the green one? Which one is more polar if I have a polar mobile phase and a nonpolar stationary phase? Okay, the answer is the green one is more polar. The mobile phase traveled faster through, the mobile phase is polar. And so the green one, spending more time with the mobile phase, means that it's more polar because it spent more time with the mobile phase. So the green one must be more polar, the red one must be less polar. And this is how we can separate molecules based on polarity. We could do this with charge. We could do this with size, called size exclusion chromatography. So again, various different kinds of ways to do this. Now, two specific types of chromatography are paper and thin layer chromatography. And they both have the exact same principle. You have some stationary phase, which is this time polar. This will either be with paper chromatography, or thin layer chromatography will use silica, which is also polar. And so you will blot. So you may have done this in middle school or in high school, where you'll take ink, usually, so let's say some Sharpie, some permanent marker, and you will blot it down at the very bottom, like such. And what you'll do is you'll take it and you'll dip it into this solvent, like this. And the solvent will start to wick upwards. And as it does, the pigments, the colors, will start to separate out based on their polarities. So the nonpolar solvent travels this time. The nonpolar solvent is the mobile phase this time. And the stationary phase is the polar one. So with that information, which one is going to be more polar? The pink one or the green one? Which one is more polar, given that I have a polar stationary phase and a nonpolar mobile phase? The answer is the green one is going to be more polar, because the stationary phase is polar and it's staying further or staying longer with the stationary phase. As the solvent wicks upwards, the pink one travels with the solvent more. One thing we can do to quantify what we're doing here is calculate the RF value. The RF value basically, it stands for retardation factor. That's what RF means. And it's a way to compare the relative solubility of a compound or the relative polarity of a compound to the mobile phase. So the RF value will be the distance traveled by the sample divided by the distance traveled by the solvent front. So an RF value very close to 1 means that the compound, the sample, traveled very well. It's almost identical to the mobile phase. And an RF value close to 0 means it doesn't really like the mobile phase at all. It just stays with the stationary phase. Okay. So with that, let's try out this problem. Okay, so what's going to be true about separations? Thin layer chromatography, the more polar substances tend to travel higher up the plate. Now we saw how in TLC, the more polar it is, the further down it stays, because it doesn't want to move with a nonpolar solvent. So that one's wrong. Number 2, you can get almost complete separation of benzene and hexane through one round of distillation. Now, they both have the same number of carbon atoms. They both have functionally, in reality, very, very similar boiling points. They're almost identical boiling points. So you're not going to be able to separate them through one round. You want molecules with very different boiling points. 3, chromatography can be used to separate proteins with more negatively charged amino acids. Yes, we can separate things based on charge. So that one's good. Okay, so answer here is 3 only, or C. Okay, so that's all that I've got for you for the Organic Chemistry 2 lecture. You can see we talked about a lot of things here, a lot of the specific reactions and again, how those basic fundamental principles of reactions apply here. We talked about the physical properties, how pH affects solubility, intermolecular forces. So those are very core things you need to understand. And then the analytical methods are going to be a little less represented, but you still should have a sense of how they do what they do. In the next lecture, we're going to start to get into the more biologically relevant context. So we're going to talk about biochemistry, and we're going to see how some of these organic molecules apply in biological systems. We're going to talk about carbohydrates, amino acids, nucleic acids, fatty acids, and other lipids, etc. So I'll see you in the next session.
For most students, and maybe you too, the CARS is the hardest section on the MCAT. It may feel like it's one of the few remaining obstacles between you and the medical school of your dreams. But as you try to prepare for the CARS, you find there is a never-ending stream of conflicting tips, strategies, and plans, none of which seem to actually help or show any results. If you feel frustrated, overwhelmed, or lost when it comes to the CARS, if you're looking for a CARS expert who has helped thousands of students achieve their MCAT CARS goals, then you found your solution. Testing Solutions MCAT CARS Bootcamp. Founded by Nick Zahner, a current medical student at Stanford with a master's degree in philosophy of religion from Harvard, Testing Solutions' approach to the CARS is revolutionary. Testing Solutions CARS Bootcamp provides day-by-day, step-by-step instruction that teaches you the techniques that produce ultra-high MCAT CARS scores. Instead of wasting your time with the needlessly complex filler that other companies try to sell you, Testing Solutions' approach to the CARS is based on the principle of minimum effective dosage. There's no wasted time, just the minimum amount of effort that is required to get you the results you want. With over 500 4.5-star reviews on Amazon, Testing Solutions CARS Bootcamp is the most trusted, proven, and effective CARS course available on the market today. You will have access to Testing Solutions' 180 meticulously designed CARS passages, the largest CARS practice library offered by any MCAT prep company in the country. Our passages are regularly rated by users on Amazon, Reddit, and SDN as the most accurate non-AAMC CARS practice passages available, consistently rated higher than Exam Crackers, the Princeton Review, Kaplan, and Next Step. Unlike some companies who prey on pre-medical student fears by charging outrageous amounts of money for their mediocre at best practice materials and courses, Testing Solutions will always charge a fair price for an amazing product. Because after all, we're not like the other test prep companies. We're aspiring doctors just like you, only a little further down the path. Let us help you do what we've already done. If you're not happy with your CARS Bootcamp for any reason, we offer a 100% money-back guarantee, no questions asked. You've got nothing to lose and the CARS score of your dreams to gain. Don't be one of the people who write us each week saying they wish they had found our MCAT CARS Bootcamp sooner. You don't have to struggle with the CARS any longer. Sign up and get started today.